So we have a new assignment that was posted. Did people get a chance to take a look at that? See if you have any questions about it? I just kind of wrote it up. And every time I do this for the first time, there's frequently some kind of either miscommunication or misinterpretation of what I intended. So at some point, before you get started on it, go ahead and just take a quick look at it, see if you have any questions about it, and I can answer those questions. Then, see, we are 2 weeks out now from our next exam. I'm planning to give back the exams. The last person took it yesterday. And that is in the process of being graded right now. So it's just that one exam. I could probably go get them and hand them back now, but we'll go over it on Monday. The grades are available. So if you haven't had a chance to stop by my office and take a look at it, you're welcome to do so. And then we'll officially go over it on Monday and get any answers to the questions done on recording. All right, last we talked, we were discussing binary search trees, insertions and deletions. So we talked about inserting into the tree. How do we actually go do that? How do we find in a tree, given that we have a query, we want to say, is this in the tree? Yes or no? As well as the 3 cases for deletion. So we looked at the easy case of deleting a leaf, the pretty easy case of deleting a node with 1 child, and the much more difficult case of deleting a node with 2 children. What I'd like to do is have a better visual of what it's like to delete with 2 children, so I will make sure that you have that before I assign anything about binary search trees. My goal right now is the assignment that I just gave, I'm gonna have that due Wednesday so that I can assign something related to binary search trees that will be due the following Wednesday. I will get the TA to get that assignment turned around really quickly and put trees on the last exam in the class. Since we don't have a final, the material that I really need to get through to have an exam on is going to be trees. So we need to get through the material, get you an assignment, get the assignment due, and get you feedback for that by the time we take the next exam. So that's kind of sets the pace for this assignment, which means that it was a 6-day assignment rather than, I said, about a week, and I really wanted to give until Friday, but then I thought there's no way I can make something due and then put any reasonable questions about trees on the next exam.
Did the trees assignment from last one?
That's a great question. I may have something due, an assignment due that last week. So the material that we'll be covering between now and then would be heaps. The actual implementations of sets. We talked about sets, but we haven't talked about how they're implemented, and maps and how they're implemented. And then as we have time, graphs, just kind of introducing people to the topic. So I'll make a decision about that in the final week. But I would like that to be kind of the most hands-off week, because I know it's the most hands-on week in a lot of other courses. And I try to, wherever I can, put the difficulties of applying classes where other classes are going to be letting up, just to kind of create balance, so they aren't all coming down on you at the same time. Maybe that is definitely an option. Next test will be at the end of week 9. I know we don't have class the Monday of week 9, that's Memorial Day. But we'll get there. So yeah, it's a week from next Monday that we don't have class. Yeah, that Friday of week 9. So 2 weeks from today is the last exam of class. All right, so did people have any questions about deletions or want to go over some of the deletion concepts again? How are people feeling about deletion?
We should go over how to delete the node with 2 children.
Yeah, let's get an example of deleting with 2 children. So we need some kind of fairly deep tree to really see how this works. So let's draw out a tree with not just 3 layers, but 4. Let's actually give these some values. So here would be a perfectly 1 to 15 binary search tree. So if we start at 8, ask if the query node is less than 8 or greater than 8. If it's less than 8, we go to 4. If it's greater than 8, we go to 12, etc. But now we want to delete. Which do we want to delete? Do we want to delete 4 or do we want to delete 12? I think that'll be that'll show us the most from this process. Well, we'll delete 12. All right, so we want to get rid of 12. We can either bring up the 10 or bring up the 14. Usually we bring up the lesser child in practice, but you can bring up the greater child. It doesn't really matter. Anyone have a preference? What do we want to see? 10. Bring up the 10. So as we bring up the 10 into this node, we made a couple of problems in this tree. The first is that 11 is down the left subtree of 10, which is bad. This is why we need to orphan 11 and reinsert it. So we need to sever this connection. And then we need this connection to bypass this now empty node. So the new left child of 10 is going to be 9. I'm going to draw that here. Note that if there was anything in 9's left subtree, that's now perfectly fine, because it was greater than 8 before, and it was less than 9 as well. So that entire left subtree is valid. It's just that this right subtree is not. This is the problem. So where should this 11 go? Yeah, and the way we can do this is if this was the node that's going to be deleted. So this was our parent, this was our child. We don't really need access to the parent for the 2-child delete. This is the node that we want to delete. We've successfully done this. But if we go from this node and we go right and then left some number of times, we use the star to represent the star closure of that, to just say we go left some number of times, however many times there is a left child. So we go right once. We know that right exists because this was a 2-child delete, which means it had both a left and a right child. So this right must exist. Then we need to go left as many times as we can. We can go left from 14 to 13, and then we don't. That's always where this 11 is going to go. So we now reinsert the 11 and the entire subtree of 11 as the left child of that. And if 11 had children, they would also go there without having moved. So that entire subtree just gets reinserted. Right, left, 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 left. As soon as there's a null, reinsert this subtree that was orphaned right there.
Are we permitted to have duplicates in this structure?
You can. If you do, then you just have a way that duplicates are, so left would be less than or equal to, or right would be greater than or equal to. You wouldn't want both. You just need to be consistent about which one you choose.
So if there was already an 11 there, and we were still removing the 12 and adding another 11, we could do that.
Yeah.
Probably not.
Yeah, exactly. This will always work regardless of if there are duplicates or not. I probably won't ask you to do anything with duplicates in this class, but in practice, you absolutely have tree structures with duplicates. Questions on this particular example of a 2-child delete? Does this intuitively make sense? If we had brought up the right instead of the left, it would have been this 13 that got orphaned. So it's just a matter of attaching the 13 down the left, right, 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 right. This just changes. If you're doing the right, this becomes left, right star. Instead of right, left star. You go down the left, right, 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 and that gets you the next largest element. So the next smallest element from what was here, and that's where this is supposed to go, because this will always be wrong. If this is now 14, then 13 no longer goes down the right subtree of 14, it goes down the left subtree. But what's here is going to be the next smallest thing from here, so you can go reinsert that subtree at that point. So that is two-child delete. In the grand scheme of things, it's not too bad. But it's definitely harder than anything else related to a basic binary search tree. Until you get to balancing, balancing gets harder. All right, the next thing we're going to talk about are traversals. So we have an existing tree structure. The question now is, how do we do things in this tree structure in order to get certain benefits out of the tree? So you can, if you imagine printing the nodes of a tree, we can print the nodes of a tree in different orders and in different ways for different outcomes. So a traversal is just some systematic or algorithmic way of traversing all of the nodes in your tree structure. And I think we're going to talk about 3 or 4 of them. The first is called preorder. So in general, it's implemented recursively. So preorder says you're going to visit the existing node. Then you are going to do a preorder traversal of the left subtree of that node. And then once you return from that recursive call, you will do a preorder traversal of the right subtree of that node. And that's just defined recursively. So let's take a look at, again, that same tree. I'm going to redraw it without the deletion. Let's play recursion. It's a game that nobody really wants to play. We're going to play it anyway. If we do a pre-order traversal of this tree, what are the order that the nodes get printed out in? Take a few minutes, take out a piece of paper, open a notepad related app, word processing app of some kind, and see if you can come up with it. So we're going to visit the node, do a pre-order traversal of the left subtree, do a pre-order traversal of the right subtree. So what's the first node that gets printed? To give you one iteration of this. The root. So the very first node that's going to get printed is 8. The node of this entire pre-order traversal. The pre-order traversal of this is print this node, then do a pre-order traversal of this subtree. Once that returns, once we finish that entire process, we're going to do a pre-order traversal of this subtree. Have at it. Think we have an answer? Yeah. Yeah, have answers?
Yeah, do you want me to share or wait a second?
Let's, of the two of you, which would like to share more?
Why don't I do one?
Would it go like 4, 2, 1, 3, 6, 5, 7?
4, 2, 1, 3, I think it's 6, 5, 7.
Yeah, so then go to the other side, 12, 10, 9, 11, 14, 13, 15.
That is right. Well, actually, it's no left, right, but
I mean, you could do it the other way too. I mean, yeah,
that was a terrible attempt at a joke.
I'm on,
That's right, actually, that's no left, right.
I'm on 3 hours of sleep. It is actually.
I'll add that into my database.
I got that too, but, we were talking, and so would it be wrong? I guess not really wrong, but. If it went like 4 and then you check the 2 and then you check the 6 and then you move down to the 2.
That would be wrong for a pre-order reverse. We have to go all the way through. So when we do 4, we output 4, and we have to do the entire pre-order traversal of the left subtree before we do the pre-order traversal of the right subtree. So we need to explore this entire subtree. We need to output 1, 2, and 3 in some order before we output 6.
How does it check the grade?
How does it check the 3 and what, sorry?
Because I was checking the left.
Because then it's done. So let's actually go through this process step by step. I think that will help clarify. So we have the 8, great, we output it. Now we're going to do a pre-order traversal of the left subtree of 8. And we're going to put on hold the right subtree. So we're going to output everything from this subtree before we output anything from this subtree. So we see that we can break this down into node, left goes up to 7, right is here. So here is from the first level's perspective, we have the node, left, and right. The left subtree of this, we're going to output the node, the 4, and then we're going to do the left subtree of that before we even touch the right subtree of that. So here is the node, left, right of the next layer. So we're going to do the left subtree before we come back and worry about the right subtree at all. So we're going to head on in. Here is the node, left, right of that layer of recursion, or that level of recursion. So we're going to output the 2 first, followed by the left subtree, followed by the right subtree. We recurse and we go to the 1. We're going to output the node, and then the left subtree is null. So we're going to come back to the 1, and we're going to query the right subtree. That is also null. So we're going to return, and now that we've done the entire node left, right for 1, we're going to return. When we return, we're finishing the left subtree of two. So the next thing we're going to do is pre-order traverse the right subtree of two, which gets down to an outlet, the node, the three. The left subtree of three, which is null, and the right subtree of three, which is null. We then go back to the three, we're done. We go back to the two, we're done. We go back to the four, and now we've done the left subtree of the four. So the next thing to do from the perspective of the four is to go through the right subtree. So we're going to do that, and we restart from scratch. So we output the node that is the six, then the left subtree that is the five, and then we see null and null, so we return. The last thing we did at the six was the left subtree, so we need to do the right subtree. We output the seven, we check its children, see that those are null. Done, come back to the six, done, come back to the four, done, go back to the eight. And now we've explored the entire left subtree from the eight's perspective. And now what we have to do is exactly what we did to this left subtree, to the right subtree. So as we go to the 12, we're gonna see that this is node left, right. From the perspective of the 12. When we go to the 10, we're gonna see node left, right. When we go to the 14, we're gonna see node left, right. And that's how this completely breaks down recursively into the output that we see. And hopefully, if you've been struggling with recursion and thinking recursively in the class, hopefully this helps to visualize what recursion is doing, because we basically have this tree broken down into these three pieces. This tree broken down into this and these pieces. And then from each of these four triangles, we have the node left, right. We have the node that we output, followed by the left subtree and the right subtree, the left subtree and the right subtree, the left subtree and the right subtree, the left subtree and the right subtree. So I've made a mess of my diagram, but that's kind of how we're kind of zooming in. It's kind of like a fractal, where we have a large tree. We're going to zoom in on the left subtree and zoom in on the right subtree, kind of side by side. And as we do this, we're going to zoom in on its left subtree and right subtree. And if we look at that, we're going to zoom in on its subtree, left subtree and right subtree. So very much like a fractal. Questions about pre-order traversals? Why we got the answer that we did? How we traced through this program recursively? And how this entire process is 3 lines of code, regardless of the size of the tree. Crazy. No questions? All right. This is pre-order. Let's learn the next traversal type. Post order, which says, do a post order traversal of the left subtree, then do a post order traversal of the right subtree. And then finally, visit the node. So LRN is the shorthand instead of NLR. We go left first, then right, then visit the node. So I'm again going to draw our base tree. A little bit bigger this time so that it's easier to see. Go ahead and do the exact same thing. Give me the output of a post order traversal. What are the order that the nodes are output in? You think we have it? Yeah. What do we get? Who wants to share?
So it's 1, 3, 2, 5, 7, 6, 4, 9, 11, 10, 13, 15, 14, 12, 8.
That you said? That is right. Well, it's left, right, no. So how do we know, or can someone explain this process recursively? How do you think about this recursively? Or walk me through the recursive procedure for why this output is correct?
You go to the bottom and leave nodes, and you work your way back up to the parents.
Yeah,
And then if you have a parent node that's got 2 filter, then branch down further, you go down that other branch first before you go back up to that parent.
yeah. So it's the same kind of path that we did before. We're doing the left, right, just like we did the left, right here. Except that the node is output afterwards instead of at the beginning. So we kind of see that instead of 8 coming first, 8 comes last. But the left portion of it is still the same left portion, but it's gonna be in a different order because instead of printing the node out first, the node gets printed out last. So we see that we have up through 4 being the last thing here that's in the left subtree. We have the left subtree, we have the right subtree, and we have the node at the end, and it's just like before, it's very recursive in nature. Here, we're gonna have the left subtree, 1, 3, 2, the right subtree, 5, 7, 6, and the node, the 4. So it's recursive in exactly the same way, we're just going through it in a different order than we did before. So pre-order and post-order, you can just think of left always comes before right. It's just a matter of pre-order tells you the node comes pre the left, right. Post-order, the node comes post the left, right. And that's the easier way to remember, just based off the name, what pre-order and post-order mean and how to interpret them. So it's the same kind of recursion that we had before. Can anyone think of any applications or reasons that we might want a pre-order or a post-order traversal? Yeah,
I was trying to do a leak code problem where you had to figure out if like strings were made of smaller strings. And I didn't do it because it was really hard, but what I was trying to do was like, you make a tree and you're like literally storing like what makes the string in it, and then you have to traverse the whole thing and like
Yeah.
figure out if it's built out.
absolutely. You could store strings as substrings like this. So you could do things like, imagine that this is the layout of a paper. We have section 1 and section 2. Inside of section 1, we have chapter 1 and chapter 2. Inside of section 2, we have chapter 1 and chapter 2. Inside of chapter 1, we have 1.1 and 1.2, etc. And so how do you read this structure? It's kind of a node left, right. You read the title. This is the title of the book. You're gonna start with everything in the left, and then you're gonna go on to the right. I read, this is section 1. And I'm gonna go on to chapter 1, and once I'm done with chapter 1, I'm gonna move on to chapter 2. So there are different algorithmic reasons that we have these particular kinds of traversals, and you will find that these traversals make sense in different domains where you're storing different kinds of data in your tree, and you want to output that in some certain fashion that makes sense given that application. So pre-order and post-order are both very common. Questions on post-order traversal? Next one, in order. We are first going to do an in-order traversal of the left subtree. Then we are going to visit the node, and then we are going to do an in-order traversal of the right subtree. Go ahead and tell me the order that these are output in. Anyone see the pattern yet? Yeah? Numerical order. If this is a binary search tree, we know that the left subtree is less than the node, which is less than the right subtree. So an in-order traversal gives you the natural order of whatever is stored in this tree. So from 8, left subtree, we get to 4, left subtree, we get to 2, left subtree, we get to 1. So we're gonna output the 1, move back, output the node. Output the right subtree, which gives you left, which is null, node, which is the 3, right, which is null, back, back. This is the left subtree done, so we're going to visit the node, output the 4, go to the left subtree, the first thing we do, sorry, right subtree. First thing we do in the right subtree is visit the left subtree. Left is null, null is 5, right is null. We've done this and now visited the left subtree, so we output the node, and then we visit the right subtree, left, node. Right is null, done, 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 we've done the left subtree of this. So we output the node. Because of the right subtree, first thing we do in the right subtree is go left, left, output, back, output, right, output, back, back. Output. Right, left, output, back, node, right, output. And so we get everything in order. So it's obvious by the name that it's asking you for whatever the natural order of the binary search tree is. The pre-order didn't do that, the post order didn't do that. There are different applications for those traversals, but in order is also a very important order if you want to print things out in order or visit things in order. Questions on an in-order traversal? So the first 3 of these have been recursive in nature, and you can see how this is subdivided into those subproblems. The left, the node, and the right are always like that. So shorthanded, this is LNR for in order, we left, node, right. The last one we care about is the only one that's not naturally recursive, which is level order. So we start at the root, and we saw this before when I called this a breadth first search. We're going to do a level order, outputting things in the order of the level. Start at the root, add all of its children to a queue. And then you're going to, until the queue is empty, dequeue. And then enqueue the left child of the node, if it exists, and enqueue the right child of the node. And then you repeat that process. Dequeue and visit the node at the front, add the left child, add the right child. So we call this a level order traversal. Let's actually draw it out and see how it outputs. So I kind of like to draw queues like this. You can imagine that stuff goes in, stuff comes out. They enqueue on the right and they dequeue on the left. So we're going to start by visit the root, which says that we're going to output it. So visit the node, dequeue it and output it. NQ the left child of this node, which is the 4. NQ the right child, which is 12. Looping around, visit the node at the front and DQ it. So we're going to output the 4. And we're going to NQ the left child of the 4. And the right child of the 4. Looping around, visit the node at the front of the queue and DQ it. So we're going to visit the 12. That tells us to output it, add its left child and right child to the queue, which puts 10 and 14 in the queue. Looping around, visit the node at the front of the queue, which is the 2. We're going to output it. We are going to NQ its left child and right child. So we put the 1 and the 3 in the queue. Looping around, DQ 6. Add 5 and 7 to the queue. Looping around, DQ the 6. We already did that. DQ the 10. Output it. Add 9 and 11. Now I'm just gonna kind of draw this. This is why we want a circular queue. This is kind of like a circular queue. I should have drawn it as a circle. I think that would have helped you visualize the concept of a circular queue, because now we kind of have to loop around. But when we output we did the 11, we're gonna do the 14. You need space for the 13 and the 15. I guess we could still technically have space for them, but you could easily have a front pointing somewhere and then loop around and have a rear pointing somewhere, and that's the concept of the circular queue.
Shouldn't the 9 and 11 gone in the queue?
Yeah, they should have. They were there though, right? We already visited them.
No, not yet, because we haven't even outputted the 5 and 7 yet.
Good call. We haven't gotten to that point yet. So yeah, this 14 and 1. Well, yeah, that is the idea. We haven't done this yet, but yeah, the 9 and the 11 should be here. That's why I was doing this in the first place. Yeah, 9, 11, 13, and 15. We'll do it that way. So yeah, now we output the 14. Add the 13 and the 15. Loop back around. Done the 14. And now we just have everything in the last level to go. We're not going to be NQing anything else. We're just going to be outputting everything in the last row in the order that it appears in the queue, which is the order that it appears in that last row. So we output 1 NQing nothing, 3 NQing nothing, 5, 7, 9, 11, 13, and 15. So this would be a level order traversal. And you see that the way that it was printed out, we have the 8 first, then the 4 and the 12, then the 2, 6, 10, and 14, then the 1, 3, 5, 7, 9, 11, 13, and 15. Questions on a level order traversal? Done as a loop, not recursively, done as a loop with a queue.
So
Yeah,
the first 3, is it going 8's being DQ'd into the, or is being added to the front of the queue?
yeah, basically you start with NQ8 and then loop. So yeah,
Or,
yeah, NQ the root and then loop, DQ add left, add right.
so once you,
Add left, add right.
so once you add the 4 in, 8's being DQ'd out, and then once you add the 4. Or I guess then once you add the 12, and then the 4 is being DQ'd out?
Yeah.
Okay.
Yeah, so you would start with the 8, DQ the 8, add 4 and 12. DQ the 4, add 2 and 6, but after the 12.
Okay.
DQ the 12, add 10 and 14. So now the queue contains the next row. By the time we finish any particular row, the entire next row is in the queue. The issue with this is that we need an amount of memory that is proportional to the size of the last row, and each row is doubling in size. So we end up needing more and more and more and more memory as we get deeper into the tree. But to output in level order, we need that. That's just one of the detriments of outputting in level order. Good questions. Any more? Yeah,
You will always just all the children in the tree, with it like dynamically updated.
it's being updated every pass through the loop. But yeah, it's gonna always contain the children of the nodes that haven't been visited yet that are in the queue. So as we DQ one node, we put its children in, which means that every time we DQ one, we NQ two, or up to two, depending on the tree. If I asked you to write code for these, how do you think it would go?
I think I could do this one, but maybe not the recursive ones.
The recursive ones are the easy ones, because they're only 3 lines. This one's actually the hard one. It may be the more intuitive one, given your experience in 210 and 211, but it's the recursive ones. As you start thinking recursively, you go, whoa, when this can be easy, it's really easy. If we look at, like, for instance, the in-order traversal. We would have something like in order root. It takes the root as the parameter. So do an in-order traversal of the left subtree. This would say the first thing we should do is call in order and pass it root dot left. This makes the new root of the new subproblem the left child of the current. Then we want to print out the data of the root, root dot key. Then we want to do an in order of root dot right. There's something that I haven't checked for that's really important. What is it? We know there's a root by calling it, but we don't know about the dot left and dot right. So what we really need to do for this is to surround them with if statements. It says if root dot left is not null, do this on root dot left. If root dot right is not null, call this on root dot right. And that way we skip over them if they're a leaf. And that's what gives us our base case. Our base case is a leaf node where there is no left and there is no right. So slightly more than 3 lines, but this is the basic idea of what in order does. We just need an if statement around the 2 calls to make sure we're not dereferencing null. The other way you can do this is there is a root dot left that just will be null, so we can check if root is null. So you just say, the even shorter one is if root is not null. Done. So that's the entirety of the in-order traversal. The pre-order and the post-order are just changing up the associated lines. So a pre-order would do left, right, node, which means that we do the left recursive call, then the right recursive call, then the print of the root dot key. The post-order That's what I meant. The pre-order is the root dot key, then the root dot left and the root dot right. So it's just changing these three lines, ordering them slightly differently, and you have all three implementations. It's really nice, very easy code. Questions on the remainder of traversals? Right, basically, oh yeah, question.
So if it's not a binary tree, could you do something like pretty similar?
Yeah, you just, instead of assuming that there's a dot left and dot right, you
You
just
have-
would say like a for each.
Yeah,
For
yeah.
all of the children of that node.
Okay.
Yep, that's exactly right. All right, we're out of time for the day, but hopefully this was useful. It will certainly be useful for the assignment after the assignment that is assigned now. Box hour starting out, you might help getting started.
Yeah. These guys, I was reading. Because I was curious about where trees were actually used in the life.
Everywhere.
I just looked it up in the sense that the one that stuck out to me the most is that trees are used for the